welcome to all of you that are here today, and I'm happy that you joined us. So I'll go ahead and get started. Okay, I see there's already one question in the chat, has something to do with if you have plugins which don't require R, like the plugin bundle, can I use Peacock with the R directory? Will there be any conflict? Yes, that's a good question. Short answer is that you can use other plugins that don't require R. So for instance, for those of you that use the plugin play bundle, it basically comes with a configured R for use with those plugins. But if you do decide to use other plugins outside of that bundle, so let's say you install something like Euclid or Peacock, like what we'll be talking about today, it won't interfere with that bundle. So that any plugin in the bundle will use the R that comes in the bundle. Any other plugin you install after that will just call to the R that's installed on your computer separately. So the one that has the R path directed in your preferences in FlowJo. And I'll talk about that once we get to the software. But the short answer is no, you shouldn't have any issues. All right, well, let's go ahead and get started. So today we're going to be talking about a cleanup tool. So I thought it would be nice to kind of lay the foundation for, why we need cleanup tools in the first place. Why do they come into play for flow cytometry data? So when we're talking about cleanup tools and getting high quality data, it's really an effort to try to remove anomalies in our cytometry data. And when we talk about anomalies, we're talking about erroneous events that arise really from technical issues at the instrument. So there's a lot of standardization and calibration that happens at the machine to make sure that it's always performing at its best. And that we don't end up with, massive batch effects. And of course, we also need things like good compensation, good panel design, and smart experimental design. But aside from that, things can happen at the instrument. Sometimes they're out of our control, but we are aware that these kinds of technical issues can cause problems with our downstream analysis because they introduce kind of these questionable events. So what are some things that can happen at the cytometer that introduce these anomalies or erroneous events? Right, we can have changes in flow rate, whether it be intentional, right? You start bumping up the flow rate at the machine during acquisition of the sample. So if you're having an increase in flow rate, that could impact the signal intensity for different parameters in your panel. There could also be an unintentional surge in the flow rate if you have some kind of a clog in the sample. And then you kind of have maybe this surge in event uptake, which might eventually return back to the way it started. But nonetheless, you have this temporary surge that might wreak havoc in the rest of the data. You can also have fluctuations in signal, which could come from flow rate. They could come from other sources, maybe some kind of a problem with the machine, or there's some kind of a contamination in the machine. So the person before you used a very intense dye, and they didn't go through a very rigorous cleaning process. And so you come in with your sample, and you might be introducing kind of an artificial introduction of this fluorescent signal that is also in your panel, but it's kind of doubling up from the previous run. And you can also have fluorescent events outside the dynamic range of the instrument. So if they're far positive or far negative outliers, and they're not kind of fitting the distribution of the rest of the data from the run. Okay? So all of these different technical issues at the instrument can introduce what we call anomalies. So data that are questionable, don't follow the norm of the rest of the data. And really the dangerous aspect of these is that they can introduce false discoveries into our analysis, right? And give us a false impression of what's actually happening in that data set. So let's look at some maybe examples where these anomalies might wreak some havoc, right? So here we're trying to illustrate the importance of high quality data and how if you don't do a good cleanup or do at least some cleanup on your samples, you can introduce anomalies that lead to false discoveries. Okay, so this is a series of flow plots that I actually took from a publication describing the Flow AI cleanup tool. And here they're showing an example of a flow cytometry data. And here we're looking at CD3 signal and over forward scatter. And we can see that there's kind of this CD3 dim population, right? So I might see this population unique to a couple of samples and might interpret it as a novel phenotype and this CD3 dim population is somehow associated with a control of an infection or desirable outcome after some kind of a treatment administration. And so I give a lot of focus to that cell type, the CD3 dim cell type that's only present in some of the samples. However, if we start to focus in on that sample and look at that parameter over time, we can see that at the beginning of the acquisition, there was kind of this abnormal event where I had this kind of temporary shift in the CD3 signal. And so if I draw a time gate to exclude that region, right, because we can see it doesn't follow the norm of the rest of the run, your samples are homogeneous, so your signal should be stable throughout the whole run in theory. Right, so if you have a period of instability like this, it could have been caused by some kind of a problem with the laser or some kind of a surge in flow rate. But nonetheless, we don't want to incorporate this region because it's unstable and it's unreliable. And so if we draw a time gate to exclude that region, you can see that if we return to that same display as the first plot, that phenotype has disappeared. Okay, so really just illustrating the point that without this inspection, a user may have made some kind of false assumptions about the presence of cell types that aren't really there. They're largely attributed to some kind of anomaly at the instrument. Now that could be with a manual approach, right? So you might think that you can just kind of keep an eye on the data and with manual gating, you'd be able to, exclude those kinds of regions. And if it's a small enough panel, maybe it wouldn't be as much of a concern. But if we're entering into this era of high parameter analysis, a lot of times we're wanting to automate aspects of our discovery-based approach. Right? So one popular tool in high parameter analysis is to do clustering, right? So with clustering, we're doing the unsupervised identification of populations in our sample to save us the time of all this manual gating, right? So this is actually a plot that I took from the publication describing the tool that we're going to be talking about today. And here we're illustrating the importance of, again, of quality control and what can happen if we don't do quality control on our samples and start to do these unsupervised analyses. Right, so here we're looking at two parameters over time, right? Again, it should in theory be stable over time because the sample is homogeneous. But you can see at the beginning of the run, right, there was kind of a shift in signal being shown in red for the G710 parameter, right? And at one point it returns back to normal, but at the beginning, there is kind of a drop in the intensity of that parameter. Now, if we take this data and do clustering analysis on it using FlowSum, you can see that we get a lot of clusters that can be found throughout the whole run, but we get one cluster that is actually largely attributed only to cells that were acquired at the start of the acquisition, right, when it was still unstable. So what this could do is introduce, again, a false discovery where I might see this unique cluster and give a lot of attention to it, phenotype it, look at its frequency between samples. But really this cluster is an artifact, right? It's an artifact of the unstable period at the beginning of the acquisition run, right? And this cluster isn't really attributed to the rest of the sample collection period where it was more stable, okay? So again, dealing with an artifact and not a true biological finding. Now, what can we do to prevent these kinds of things from happening, right? What kind of approaches in FlowJo are there, if this is where you're going to do your analysis, to be able to assess the quality of your samples and ultimately target it for cleaning, right? So there are some native features within FlowJo to be able to assess the quality of your samples. So there is an inspect button at the top of the workspace that allows you to inspect sample quality within the software. So when selecting a sample and launching that button, it'll basically open a large properties window, but I just took a zoom in screenshot here to focus on one main concept, and really that's signal stability over time. So what we're looking at is each of these parameters over time on the x-axis, so parameter on the y-axis, time on the x-axis. And again, in an ideal world, that signal would be stable across the entire period of the acquisition because it's a homogeneous sample. But again, technical issues can happen at the instrument, right? We can have surges in flow rate, we could have signal instability, et cetera. And so what you're looking at is your signal stability over time on the green line. And ideally, you would have it be very close to the median for the rest of the run, which is represented by the dashed line. And we have some standard deviation boundaries here to kind of give you an idea of how much that signal is fluctuating. So we have +2 standard deviations at the top, -2 standard deviations at the bottom. Okay, so ideally, we'd want that signal to be nice and stable along the median, but there could be situations where the signal either approaches the standard deviation boundaries or even exceeds it. And so those might be areas that you want to exclude from your analysis, right? And use this information to kind of move forward with a cleanup. Now, another aspect of the software that can help you assess the quality of your samples is the check sample quality function. Okay? So using the information to some degree that was on the previous slide, when you hit the check sample quality button in FlowJo, you can have one of these badge colors assigned to each of your samples to give you kind of a rough benchmark of what the quality of those samples are. Okay, so there's one of 5 possibilities. And basically you can think of it as a stoplight, right? Green being best, go ahead with your analysis, maybe, still do some cleanup if you'd like to. And then going all the way down to red, stop, this sample might be unacceptable for analysis because it has a high number of flaws, okay? So when we talk about flaws, we're talking about these kind of events of deviation away from the median, okay? So the more of those deviations you have, even if it's only for one parameter, right, the worse this score will be. Okay? So green, again, very little to no flaws, and all the way down to red, which means the highest level of flaws available. Okay? So again, sample cleanup is always recommended, no matter what the badge color, right? Because even if we're looking for rare cell populations, they could very easily fall within an anomalous region in the data from acquisition. But we would especially recommend cleanup, right, as you approach some of these kind of more warmer colors. So how can we clean up the samples in FlowJo, right? So historically, folks have always used time gates, right? So with manual time gates, we can exclude periods of instability. Okay? So if we look at this example here, if I have concerns about the stability of the forward scatter parameter over time, especially at the beginning of the run, and maybe again towards the end, I could use a time gate, exclude that region of events, right? And then take the events within the kind of high quality gate and use it for downstream analysis, right? So from this stage, I would move forward with my, scatter gates, my viability die, and all of my major populations. Now, there's nothing wrong with this approach, right? We've used it for a long time, and it's definitely better than having no cleanup approach at all. But, again, it is not the most efficient way as we move forward into these larger panels and larger data sets, right? So for a true comprehensive cleanup, you would really need to check all parameters for each sample. I think there's a habit to just check 1 or 2 and kind of apply the same gate to all the samples, right? But really that time gate is unique to that parameter. It's also unique to that sample, right? So really you should be doing this check across all your colors, across all your samples, which again, if we're dealing with a large panel and a large number of samples, you can imagine how time consuming something like this would be, right? To invest the time to just draw these quality control gates before you even move forward with the rest of your analysis. So is there another way, right? Can we automate this process in some way? And the good news is we can, right? There's a number of quality control and cleanup tools out there for use outside of FlowJo even. There's probably even a larger number available in such as the R statistical environment, for instance. But the 3 that are available in FlowJo, one of which we're going to talk about today, is FlowAI, FlowClean, and Peacock, right? Newly released last week. Okay. So whichever cleanup tool you use, they basically operate in the same way and give you the same endpoint. Okay, so you can feed your files into each of these plugins, and the plugins are going to inspect the FCS files for these anomalies, right? Each one has different ways of, calculating what exactly an anomaly is, right? It has a different way of inspecting the files, but it does the inspection. It's going to remove those anomalous events or bad events, and it's going to return high quality events or good events, right? So you'll get 2 subpopulations in the workspace. And you could do an overlay in the layout editor like this just to kind of visualize what ultimately got cut. But essentially what you really need is the good event subpopulation, and that's what you would continue your analysis on. Okay, so whatever tool you use, it's basically going to have the same endpoint. All right, but again, we're here to talk about Peacock today, so I'm going to just spend a little bit of time talking about this tool before we move into the demo. So PeacoQ, or Peak Extraction and Cleaning Oriented Quality Control, is a cleanup tool that uses density peaks per channel to remove low quality outlier events in 2 different filtering steps. Okay, and I'll talk about that on the next slide. Now, if you'd like to learn the details of this tool, I'd highly recommend reading the accompanying publication, right? So I'm going to do kind of a high level overview today, but if you'd really like to learn the details and the recommendations for its use, I'd highly encourage you to read the paper. So in addition to removing these low quality outlier events, based on basically their deviation from the rest of the data's peaks, it also flags for monotonic changes in signal, right? So we might have a situation where we don't necessarily have a temporary shift in signal, but over time we can see the signal kind of gradually increasing or gradually decreasing. And we'll see some examples of that in a second. And it doesn't remove these regions, but makes you aware that they are present and for which parameter they're present for. I think one of the best features about PeacoQ is its ability to be applicable to a wide variety of data sets, right? So as we'll learn in the next couple of slides, and as is better described in the paper, these parameters for how this tool is run has really been, widely tested over different data types. Right, so we typically deal most often with, traditional or conventional fluorescent cytometry data, or even spectral cytometry data. But a lot of previous cleanup tools kind of left mass cytometry behind, right? So those scale of those values and the kinds of values we get from mass cytometry data can be quite different with what we get from fluorescent cytometry data. And it's really been kind of a challenge to use quality control tools on these kinds of data, just because of the way the values come through after the run. But this tool has really made a nice stride to try and incorporate that into the fluorescent cytometry world, where more tools are available. Also, it does a fast computation on large files. I think these cleanup tools can have a reputation for being a little slow, especially as the files get larger and larger. But I think this tool has done a nice job of increased speed time, especially as the files get larger, over 1 million events. All right, looks like we have a question in the chat. What are the good technical computer parameters in terms of RAM or processor to use FlowClean, FlowAI, or PeacoQ to use the plugins comfortably? That is a good question. So really, the short answer is for any of these computational tools, whether they be cleanup tools, clustering tools, or dimensionality reduction, RAM is going to be power, right? So the more RAM your computer has, the faster computation speed you'll likely see. Okay? So the absolute minimum for a FlowJo operation is probably going to be in the neighborhood of 8 gigs to 16 gigs of RAM. Now, if you're in a position where you're going to be doing a lot of these computational tools, I'd strongly recommend investing in more RAM or a device with more RAM. Try to approach 32 gigs, maybe even 64 gigs if you can. But that doesn't mean these tools won't run on less. They'll just, you'll feel the time a little more than you would if you had a device with more RAM. So more RAM will definitely give you a faster experience. But that, again, that's not to say you couldn't run these tools on more typical benchtop devices. Now, there's also some tricks you can do to kind of, maximize the power of your computer. One is to, allocate more RAM to allow FlowJo to use, and I can show you how to do that in your preferences once we get to the software. You can also make every attempt to make your workspaces more manageable, right? So as we'll learn in the demo for PeacoQ, there's an opportunity to export your clean events to a new workspace. And that would exclude the bad events from the new workspace. And so if you exclude events you don't need, you're going to make those files smaller and more manageable. Okay? So making the workspace smaller, right? Only bringing in the files you're actually going to work with, and kind of separating them by analysis type is probably going to be also another good approach to see some increases in computational speed. Oh, I didn't realize I animated that too, but that's fun. Okay, well, let's go to the next slide. Okay, so let's take an overview of what PeacoQ is doing, right? So how is it actually cleaning these files? Like what's happening under the hood here? So the requirement for putting your FCS files into the Peacock plugin, right, or even into the Peacock tool when you're using R, is we need to do a little bit of pre-processing, right? And that's going to vary depending what kind of file you're bringing in. Okay? So if you have a cytop file, right, there's no need for compensation. That's not an aspect of the technology. Okay, but you do want to make sure, and this is going to be the case for all type files, is to make sure that they're transformed and scaled, right? And that's what we're going to call a pre-processed file that will go into the rest of the tool. Okay. Now, when it comes to a conventional flow file, one aspect is you'll want to make an attempt to remove margin events, right? So these are going to be outlier events that are at the boundaries of the dynamic range of the instrument. Okay, so you can do this inspection manually. I think there are some tools available in R to help automate this a little bit, but you could go through each of your parameters for your data and try to find these events and kind of gate them out. Right? And so after removing those margin events, we of course want to make sure the data is compensated. And I'll bring this up again later, but this is actually a unique aspect of the cleanup tool compared to the others on the FlowJo exchange, right? Those typically take uncompensated raw parameters. In this case, we're going to feed in compensated parameters, right? And that just feeds into how the tool works on the next panel. Okay. So we'll remove margin events, compensate, transform, again, pre-processed file that's going to go downstream. And then with the spectral cytometry, we're just make sure that it's compensated or more properly unmixed for that platform. And then again, transformed, and we have our pre-processed file. Okay. So for the fluorescent files, I think the compensation is the biggest takeaway here. And then for the cytop, just, transformation, much like the other two as well. All right, so once we have this pre-processed file, right, what happens next? Okay, so when you feed this file into the tool, the first thing it's going to do is bin the samples, right? And how many bins each sample gets is going to be determined based on the event number for the most part. So we assign these bins, or basically kind of these sections, right? So we're dividing the data up into these sections, right? And these bins have some overlap between them. And in each bin or each section, we're looking for the peak for every marker in each sample, right? So what's the peak for APC in each of these bins? What's the peak for PE in each of these bins? Okay, so looking for the density peak for every marker. And then when we get all of those values for every bin, right, for all the samples, then what happens is we form some kind of a matrix, right? So this is just a very oversimplified view of what that matrix would look like. But essentially you would have a row for every bin, and you'd have a column for every peak for every marker. Okay? And then looking at that matrix, we start to ask, well, how can I group together bins that are similar, right? And we would expect a lot of similarity between bins because this is a single sample, right? This would be the matrix for one sample. And so we would expect each of those bins to behave similarly, right? Because again, this is a homogeneous sample, that signal should be stable over time. But again, there could be bins where abnormalities got introduced, right? So let's say, for instance, this middle bin seems to have kind of an elevation of almost every peak, right? The median is higher in that particular bin. So it's easily separatable from the rest of the bins, right? And I might have a bin down here where it had some kind of a shift in signal for only some of the peaks, right? So using this matrix, you can kind of imagine that you're clustering together the bins that are most similar and finding the ones that are most dissimilar based on their altered signal intensity in that bin, right, for that particular marker. And so using this kind of a visualization, right, and this kind of data, then we're building what we call an isolation tree. Okay, so you can think of this isolation tree almost as kind of like a dendrogram. And we start with the root file and basically ask, well, where can I make one split, right? Where are there some bins that are different enough from the rest of the bins, right? Easily separatable from the rest of the data, because again, they have some kind of an alteration in their signal intensity. Okay? And using that, then we make a split, right? So split that bin out and then get the rest of the bins that remain. And then ask that again in an iterative process. Okay, now that I have this file, are there any outliers that can be easily removed? And if so, we remove those. Okay, and you move on in an iterative process until we end up with an end node where presumably all the bins are very, very similar to one another, right? Indistinguishable from one another based on their peak densities. Okay? And so then taking that end node, then we do one last filtering step. Okay, so this is the first outlier removal step. The second step is then using this MAD statistic or median absolute deviation away from the median. Okay, so we track the median of that peak over time for each of the bins, and then ask where there's areas where in that bin, right, that signal is a couple deviations away from the median. Okay, so if we see a deviation in that peak from the median from the rest of the bins, we go ahead and exclude that region, right? And this continues for all of the different parameters, all the different samples. And then at the end, right, the gaps are stitched together and you now have your cleaned, laundered file, okay? So just to recap, so you have your pre-processing, right, which is unique to every file type, but it ultimately consists of either margin removal, compensation, transformation. And then we take that file, it gets binned, density peaks are determined. Using a matrix, we cluster and group bins that are similar to one another, isolate the ones that are different from the rest of the bins. Building an isolation tree, we remove outliers, right, based on this information. When we have the end node, we then use the MAD statistic to go through each channel, right, so each parameter, and look for deviations from the median. We remove those bins, stitch together the remaining. Okay? And then you have your cleaned FCS file to continue with downstream analysis. All right, so how does this tool perform, right? So these are actually some plots from the publication that describe this tool. Okay, so first we're looking at cleaning of samples with speed changes, right? So here's one sample where we have some speed changes that were introduced in 2 segments, right? We go from low to medium to high. And you can see that even though we had these speed changes in this sample, right, it didn't really impact the median signal, right? So you can see for these 2 parameters here, that red line or median is actually relatively stable throughout the whole run. Right? So in theory, nothing should really need to be removed because everything was relatively stable, right? And that's what Peacock gave, right? It doesn't exclude any events. So excluded events are shown in kind of the salmon orange color. And what got kept is in the dark blue, right? And so you can see that its ability to keep what is deemed stable kind of matches what we see in the raw data. Now, by contrast, when we look at the situation on the right, again, a purposeful speed change introduced, right? We go from high to low, right? So we should be introducing kind of some anomalies in these perturbation steps in gray, right? And we can see that that happens, right? For both of these parameters, we have kind of this temporary shift in the median intensity of each of those parameters, right? So those should actually be removed from the data because they don't follow the rest of the data. And that's in fact what happens with Peacock, right? It happens to remove the data that happens to be in those same perturbation steps and preserves the regions where the signal returns back to normal. All right, so let's look at some other examples, right? So we'll talk about cleaning of samples with signal changes, right? So here's something kind of like what we showed at the start of the slides, right? We have kind of a period of instability at the start of the sample, right? So right when we're starting the acquisition, we can see kind of this spike in the flow rate. And that spike in the flow rate caused a temporary shift in signal for this parameter down here, right? And you can see that it has kind of this temporary increase that eventually does return back to what the rest of the sample looks like. Okay, so the data got removed from that portion, right, corresponding to that startup anomaly that happened. Now here, this is where we're talking about monotonic decreases or increases in signal, right? So one situation that's described in the manuscript is DAPI contamination, right? So let's say you had a user before you who had a very intense DAPI stain, and they didn't clean the machine before you got there, and maybe you didn't do any cleanup either, and your panel has DAPI in it, right? So what'll happen is at the start of the acquisition period, the DAPI will appear artificially higher, right? But eventually over the acquisition period, it's kind of returning to the rest of the sample, which really represents kind of the signal that's in your homogeneous sample. Okay. But the other parameter remains unimpacted. Okay. So when we see this drop in the flow rate here, right, that corresponds to maybe a drop in another parameter, then that area got removed by the algorithm, but it also got this warning the user about this monotonic decrease in the DAPI stain. Okay, so it's not actually cutting out this entire data set, right? Because there'd be no way to really do that because it's gradually decreasing over time, but it at least makes you aware that that is present So you can, be aware of that and possibly just deal with it accordingly in your analysis. Let's see, another question in the chat. In the high-low example, how does it know which one is normal? If the FCS files has an even split between running on high versus running on low, how would it determine which is normal? As a matter of seconds and differences. I see. So I think it has to do with this plot. I think we're talking about this plot here, for instance. Is that correct, Mickey? I'm not sure if I'm saying your name correctly. I think the question had to do with this panel B. Okay, great. Thank you. So high, low, high, low. Yeah, that's a good question, right? So how do we dictate, what's the anomaly? And yeah, I suppose it has something to do with the way the rest of the run looks, right? So here, this might not be quite an even split here. It could be that these are still the majority of the run in white, and there's a shorter perturbation period in gray. So I think it has more to do with the proportion for the rest of the run, right? And this is probably just kind of an oversimplified schematic just for display purposes. And Annalise, if you're on and you have any comments you want to expand on that, feel free to put it in the chat if you'd like to. All right, so let's see, I'm going to go ahead and move on. Okay, I think we covered that slide. And so let's talk a little about performance and speed, right? So how did this tool perform against, say, a manual inspection, right? So they did this nice assessment where they basically gave a bunch of FCS files, I think it was about 55, to a number of scientists, and asked them to clean it manually, right? Annotate regions that they themselves would remove. And then also ran those same files through Peacock, right? So based on how many events got removed by the scientists, right, they created kind of a random benchmark, right? So same percentage removed, but the regions being removed are random, right? As whether it's purposeful with the manual cleanup and the Peacock tool. Okay. So you can see in this case, it removes about the same amount as the scientists removed, right? So how many events got removed from each of the files, right? It had really nice sensitivity, so the ability to find the same anomalous events that the scientists found manually, and also nice specificity, right? So being able to not, kind of over remove events, right? So there's not an over removal things that the scientists deemed were okay. And the balanced accuracy is basically kind of a score of these two metrics. Okay? So you can see that it performs nicely in the sense that it, it removes only what kind of needs to be removed based on the human eye. It picks up anomalous events well, right, and doesn't have too many off-target effects. And in terms of speed, right, so here's some metrics they did for that compared to some other tools, right, two of which are actually available on the FlowJo exchange. There's FlowAI and FlowClean. And so Peacock is in the purple, pink, magenta color. And so you can see, right, depending on the file size, it can perform comparably to some of the other tools. In other situations, it's much faster. But I think one area that's nice to highlight is as our files get larger, right? So somebody asked earlier about computational speed, how much RAM do you need? But, at the end of the day, if a file has millions and millions of events and you want to clean all of it, you could really expect some of these tools to run for several minutes on that file alone. But if you're dealing with something like Peacock, you can see that it does have an advantage in the area of large files, where some of the other tools might fall a little short. Oh, thank you for the comments in the chat, and I always appreciate it. Okay, so moving on. All right, so let's talk about tuning some of the settings, right? So if you read the paper, I think the authors do a really nice job of describing the settings that, are called robust default settings, right? So there's put a lot of work into finding values for each of these sections we're going to talk about to ensure that they're widely applicable to a variety of data sets, right? And that way you don't have to panic so much about tuning these to the needs of your data, okay? But that being said, right, there might be a situation where perhaps the tool is not strict enough or it's too strict for your data, and you decide that you do want to do some tuning, okay? Now, I'll add that there's more tunability in the R implementation of this tool, okay, but in the plugin version in FlowJo, we picked two of the major ones, a third one, which really has more to do with file type. and brought them into the tool. Okay, but if you'd like to learn about the others in the R implementation, again, I'd invite you to read the manuscript, or we're just going to talk about the two that are in the tool for the plugin. Okay. So the first is the IT limit or isolation tree limit. So this is going to be the gain limit for the splits on the isolation tree. Okay, so you can think of it as kind of the cutoff for what we determine is an outlier, right, when we're forming that isolation tree in the first filtering step. And so the default value for that is 0.6. Okay, so if you lower that value, it's going to become more strict, right? Because you're basically saying you're allowing less deviation in outliers. So then that's going to cause more splits than you would see if the value were higher. Okay, so lowering that value will make it more strict. Then we also have the MAD number. Okay, so remember, this is the absolute deviation from the median. And so the default here is 6, right? So how many deviations from the median are you allowing? So if you will lower that value, it's going to become more strict. Okay, so if you're allowing less deviations, then you're making it more strict. If you allow more deviations, you're kind of loosening it a bit. Now, just to note that often in our plugins, if you hover over each of these input values, you'll often get a little tooltip that describes what the value is and what it does for the tool. So, take all the notes you'd like and feel free to memorize, make yourself a little cheat sheet. But just know that if you hover over each of these, you'll get a little reminder about what they do. And lastly, there's also an opportunity to indicate whether your data is mass cytometry data. Okay, so if your data comes from Cytoph or some kind of mass cytometry platform, right, we want to check this box to make sure that we handle the 0 values in an appropriate way, right? So these are going to be more common in Cytoph data. So we want to make sure that they're being handled appropriately. Okay, so that's just a check of a box to indicate if that's where your data came from. All right, and so here's just a quick snapshot, again, looking at all the different tools on the exchange and really how each of them operate, what each of them can provide for you. And that way you can kind of make an assessment of which one's going to suit your needs. Okay, so a reminder that in addition to Peacock, which we talked about today, we also have FlowClean and FlowAI. And they're different in their kind of extraction methods. FlowClean is just going to exclude bins with shifts in population distributions. FlowAI does a couple more checks. So it's looking at flow rate, regions of signal instability, as well as margin events. Okay, whereas Peacock is looking for events easily separable from the rest of the data. This is off the isolation tree and deviate from the median peak intensity using the MAD statistic. Okay. Now, while it doesn't necessarily exclude monotonic increases or decreases in signal, really, because that would be hard to approach that in a mathematical way, it does warn you about those monotonic increases or decreases in signal, whereas we don't get those same kinds of reports from either FlowClean or FlowAI. When it comes to a report, FlowClean doesn't give you anything to really look at, right? It'll give you your good and bad events. But with both FlowAI and Peacock, you do get a visual summary of the cuts, right? So it's a nice report of what actually got removed from the data. And what kind of cytometry data sets we can use? FlowClean and FlowAI work best on fluorescent cytometry data, right? Whether it be conventional or spectral. But that doesn't mean they can't be used with mass cytometry data, but they do sometimes fail on occasion. Or in the case of FlowAI, we might have to exclude some of the checks in order to get it to pass. Okay? Whereas with Peacock, it's been made suitable for both fluorescent and mass cytometry data sets. Okay, now here's another key difference down here. FlowClean and FlowAI are going to take the raw, uncompensated, or unmixed parameters, right, particularly for fluorescent cytometry data, right, because it wants the raw files before we have the confounding factor of compensation. Whereas the Peacock tool is going to use compensated parameters. Okay, so whether it's spectral or traditional, right, you need to make sure that some kind of compensation or unmixing has been applied to those parameters before you move forward with cleanup. Oh, it looks like I animated that again. Put these animations in here by accident. All right, so I'm going to go ahead and just move quickly into the software. I'll also take a quick field trip to our website to show you where you can get this tool and also where you can access this recording as well. Okay. All right, so if you go over to flowjo.com and head over to the Learn tab. So for those of you that are here today, this is where you may have heard about our webinar today. You go over to the Webinars tab. You can see not only all of our upcoming webinars, including the one you are all in today, but if you go all the way to the bottom, there's also a recorded webinars button And this is our library of recorded webinars. So today's webinar should show up right here at the top, probably in the next few days. So if you need to rewatch the video, you can do that at that point. Okay, and then in terms of accessing the tool, if you go over to the Downloads tab and go to the FlowJo Exchange plugins section, this is where all of our plugins or external tools are available at no additional cost for download. Okay. So if we quickly wanted to get to all the quality control tools, we could uncheck some of these filters, right, and quickly get to quality control. And you can see here we have Flow AI, Flow Clean, and the newly released Peacock. Okay. So when you open up that plugin card, you'll have an opportunity to learn some information about the tool, as well as those who developed it. And then you can download the tool, right? And when you download it, you'll basically get a zipped folder. If we open up that folder, inside, there will be a subfolder that contains a how-to document, right? So a very nifty instruction tool to walk you through how to use the plugin, right? And it even gives you some screenshots along the way. But also you get the jar file. So this is really what you need to use the tool. So you can take that file, drag it right into your folder where the rest of your plugins are. If you don't have a folder, you can create a folder somewhere in your documents or somewhere local to your computer, or you can make it in your applications if you have a Mac. And basically just drag that jar file right into that folder. And then I'm going to open up FlowJo to show you the next step. Right, so for those of you familiar with plugins, right, you'll know that you have to not only bring the jar file into the plugins folder, right, but also any R-dependent plugins are going to need R as well. Okay, so you can install R for free from the internet and install it to your device. Then if you come over into your preferences and go over to the diagnostics tab, here you'll just set the path to where your R is located. And we have some documentation and videos on our website to help you with this. But essentially you'll navigate to where it's located. And then you'll also need to tell FlowJo where your plugins are. Okay, so navigate it to where that folder is where you have that jar file and maybe your other jar files available. Okay, and then you'll need to restart FlowJo for these changes to save, and then you should be able to use the tool accordingly. Now I will say the first time you use any plugin, particularly if it has R dependencies, it might take an extra minute or two to run just because it's installing everything it needs. But moving forward, it should usually be a snap faster. So what I've done here is opened up a workspace and brought in a couple of different files. I brought in some cytoph files as well as some fluorescent cytometry files, just to show you the two different file types that you could use in this kind of a plugin. So if we're ready to use the plugin, right, we can go ahead and just launch it from the plugins dropdown. Now, the other thing I'll highlight here as well is that, again, you can check the sample quality natively in FlowJo, but it's not going to necessarily do any cleanup. It'll just give you an idea of the quality of your sample. Okay, so if I wanted to do that, I can navigate to the Tools tab, hit the Check Sample Quality button, and here I can see that a lot of them have kind of this magenta color. So, according to the signal stability in the Properties window, which I can launch by double-clicking that badge, right, it's picking up some periods and some of these parameters, right, that are maybe approaching those standard deviation boundaries or deviating from the mean in a significant way from the rest of the run. Okay, and so based on that number of flaws or deviations, that's where it's getting this badge score from. Okay, so let's say I've checked it natively and I've decided I want to use some kind of a cleanup tool. So we'll use Peacock today. I can go ahead and select the sample, right, and go ahead and go to the plugins dropdown, launch the Peacock plugin. Thought I could make this bigger, but it seems I can't. And it's going to automatically try to pick the compensated parameters because that's what it needs. And so you can see it's done that here. Here's the opportunity to modify the strictness of the algorithm, right? So again, the isolation tree value, if you lower that, it's going to become more strict, right? And here's a reminder for that if you hover over the input box. Same for the MAD value, right? You lower that, it's going to be more strict. Okay. You have an opportunity to export cleaned up samples, right? So basically what will happen is when the tool completes, it'll have a subpopulation of good and bad events. However, if you're dealing with kind of a low RAM device, or you just want to clean up your workspace, you can have these files sent to an output folder, and I'll show you how to get to that. And then you can bring those files into a new workspace, right? So that way you either don't get confused or you're just trying to make your workspace a little bit smaller. Okay, so that's optional. Cytop, we're going to skip that checkbox because this is fluorescent data. And lastly, save our script and output messages. The first couple times you run plugins, I always recommend saving that box there. And really that's because if you contact tech support with an issue for your plugin, if you provide them these files, it's incredibly helpful because that's where the error messages will be. So they'll likely ask you for it anyway. So you might as well just go ahead and have it at the beginning rather than have to rerun the tool just to give them that file. Okay. All right, so once you have all that checked, right, I'm going to go ahead and hit OK. Now you should see a calculating and a peacock feather show up beneath the sample where you executed the cleanup tool. And it should be done here in just a second, but what you all may have noticed in the background is a folder has been made where my workspace is saved and it has the same name. Okay, so this is your output folder. Okay, so this is where the calculations from the cleanup tool, as well as the exported FCS files will also go. Okay, so you can see the tool finished completing, right? It has my good events and my bad events, right? And so once that tool is complete, right, I can open up my layout editor and actually drag that node right in here. Okay, and that's way too big. Let's make it a little smaller. And here I can see a report of the check, right? So this sample was actually pretty clean. It only removed about less than 2% of the data, right? And you can see the region that was removed and why it was removed, right? Which filter did the removal, right? So if we scroll to the bottom, we can see good values that were kept in white, values that were removed during the MAD check, and values that were removed during the isolation tree check, right? Which in this case, I didn't have any come from there, but I did have some come from the MAD check, right? So that individual channel check, right? And I can see kind of the parameter that might have been the culprit for that, which in this case was my CD38 APC. And so it found kind of a region where there might have been some deviation from the median. So you can see that as a report, but if you don't want this in your layout editor, it is going to be in your output folder, right? So if we navigate to that folder, open it up, it'll be named after the file it was ran on. Okay, and so we can see here, these are files. Again, that'll be helpful for tech support if there's any issues. Also, the calculations from the cleanup. Also, if you double click the Peacock folder and the Peacock plots, you'll have that image as an output. Okay, so you don't have to worry about it being permanently in your layout editor. You will have it in your output folder, and it'll probably be a better resolution copy. Okay. All right, so let's say I wanted to run this tool again, right? So there's two ways I could do that. One is I could just launch it again, or you can always drag and drop the Peacock node right onto that sample. Okay, but let's say I wanted to run the second sample, but actually I want to increase the strictness a little bit. Right? So I can come in, again, launch the plugin. And this time I'm going to maybe reduce each of these by half, right? Make it a little bit more strict. So I'm allowing less deviation. So it should remove, in theory, more data, right? Maybe compared to the sample before it. Okay, so I'm going to go ahead and increase the strictness there. Okay, and this is a rather large file, or you can see it's about 1 million events. So you can get a kind of a benchmark of how long it takes on a larger file size. And I guess while we're waiting on that to calculate, I'll pause and see, are there any questions at all? Okay. Hearing none, I'll go ahead and also remind that if you do export FCS files, they will also be in that output folder I just showed you. Okay, so this is done running. So it looks like in this case, we had more removal, right? About 25% of my events got removed. So let's take a look at that report, right? Does it look any different? Right, so you can see in the case of this sample, right, I had actually get events removed from both checks, right? So from the isolation tree and from the MAD check, right? So you can see those are color coded for which regions got removed, right? You can see the breakdown of the different parameters, right? Where those checks might have failed. And so you can inspect that data that way. Okay, so you can always tune the algorithm to your needs. Okay, you can also make just a very simplified layout editor image, right? Where you could bring in your good events, your bad events, and you could look at them over time, right? If you wanted another way to visualize what got removed, but you want to look at it in a single plot instead of in a summary plot like this. And I guess I'll run one last instance of the tool. I'll run it on the cytop file just to remind you that we have a checkbox that needs to be selected. Okay, so in this case, here are my parameters, right, for the cytop run. So I'll go ahead and select them. Right, and then again, I can tune the strictness, right? Tell Peacock that this is a cytop file, right? Go ahead and hit OK. Right, and we'll see it calculate, or we see the peacock feather there. So as long as it says calculating, it is working. I will say that if the calculation disappears quickly and it just says peacock, it's likely the plugin failed because some kind of installation issue. So that's when you would contact tech support, send them those R files so they can help you. All right, and so again, this one has completed, right? A very clean file, only removed, 0.1% of the data, right? But I could always look at the report and see where that region is if I wanted to look at it. And just another tip and trick when it comes to plugins, right? If you've used this node in all the ways you want to, right? You've dragged in images into the layout editor or took another peek at the settings on how you ran it. I'd recommend deleting it after you're done, right? So you can always just right click it and hit clear. Right, and you're not deleting the data, you're just deleting the operation node. And the reason we recommend this is because on occasion, when you close the workspace and reopen it, if that node is still here, it's going to try to redo these calculations, and then the workspace is just going to kind of lag on you. Okay, so what the really important part to keep is the derived parameter, which is this blue AB symbol that precedes the algorithm name, right, which is peacock in this case. Okay. But the operation node, which usually has some kind of an icon to match the plugin name, those can be deleted. And then I recommend that you do delete them if you don't need them for any reason. Really, everything you need is the derived parameter and your subpopulation of events, or the exported clean file if it ends up in the output folder. All right, I see something in the chat. All right, so it says, looks like Peacock removes automatically, so no extra gating needed when the analysis is done. That is correct. Yes, it automatically removes the bad events. So what you would do at this stage is proceed with your gating on your good events, right? So at this point from here, I could move forward with, some kind of a scatter gate if I wanted to, or if I was going to just go forward with my major lineage population identification, I could do that. And then again, if you choose to export your good events, it'll make a new FCS file into your output folder. Then you can take those files and bring them into a new workspace and start your analysis there. But you are correct, you don't have to try to model the gating that's in this layout editor. Okay, that it has already been done for you. All right, any other questions?